from positive infinity?
Of course. The same question. What do we get?
Negative infinity.
That's it. Done. So, what am I saying here? There is nothing else I can find about the function from the function itself. I'm done. I exhausted the function. I can only find the x and y intercepts and the limits. And I just did that. Now I'm ready to study the derivative.
I have a question.
Please.
So we just did the limits, right? Positive infinity, the limit is positive infinity. Why is on the chart under negative infinity it's written?
Because I talk too much.
Oh, okay. I was just confused, that's all.
Of course. Of course. I didn't copy what I just said. At infinity is infinity. And at negative infinity is negative infinity. I didn't copy what I just said. Thank you very much.
Can I add something as well?
Of course, anytime.
So I noticed a pattern that they're both negative infinity and positive infinity. Is that always the case? Of course, right?
That is the case for odd degree. For polynomials odd degree, this will be the case. Either positive infinity to negative infinity or negative infinity to positive infinity. So this is only for odd degree, not for even degree. That will not work. For even degrees, either going from positive infinity to positive infinity or from negative infinity to negative infinity for even degree. So do not draw conclusions before you study the, a very good question, before you study the degree. And this is for polynomial. If the function is log or exponential, that's a totally different story. So this concept is only for polynomial functions. This does not work for other functions. Very good. Good. So we exhausted the function. It's tired already. I'm kidding. So now we have to find the first derivative, and then we have to find the second derivative and see what we learn from the first and from the second about the function. Can anyone differentiate this function for us? The derivative of x cubed minus 27x.
3x squared minus 27.
3x squared minus 27. And I have to set it equal to 0, or I have to set it equal to undefined. Which of these two doesn't make any sense for a polynomial function?
Undefined.
Of course. Never. Just for this function, never. Good. We're going to come back to it in a moment. So can anyone differentiate this function again to find the second derivative?
Just 6x.
Excellent. And of course, we're going to set it equal to 0 and undefined. Which of these two makes no sense? Because it's a polynomial function. Good. So now I have to solve this equation. And I have to solve this equation. The first equation gives critical numbers. The second equation potentially gives inflection points. Okay, so let's solve the first one, but I will divide both sides by 3. So I have x squared minus 9 equals 0. Can anyone quickly factor or give us the solutions, whatever you want, with the calculator, without the calculator, anything you want?
X plus 3 and x minus 3.
Excellent. So then we have two options, x equals 3 and x equals negative 3. These are critical numbers. And from here, 6x equals 0 means x equals
0.
perfect. This is potential inflection point. Potential. IP. Critical numbers, potential a max min. We don't know. Why? We haven't studied the sign of the first derivative. We haven't studied the sign of the second derivative either. So, from the first derivative, I get critical numbers, which may turn into a max min. From the second derivative, I get so-called critical numbers, if you want, for the first derivative. So I get a solution, potential IP. I don't know. But now I have to be very careful and put them in the right place in the table. 3 and -3. Careful, careful, careful. -3, 0, 3 and 0. These are the critical numbers. The derivative is 0 at -3. The derivative is 0 at 3. And the second derivative is 0 at 0. Now, the analysis. Ready? I need to find the sign. I need to find the sign here, here, and here. I need to find the sign here and here. And then I'll know what conclusions I can draw. Before that, I need to find this y value here. I need to find the y value here. So I have to plug in -3 in the original function and 3 in the original function. Okay, I go back to y equals. I put in the function of interest. Clear, where is my clear? Clear and clear. Good. So the function is xq minus 27. Minus 27x, I meant to say. And then I go in. All I care about is -3 and 3. So 54 and -54. So 54, -54. Perfect. That's all I needed. Now, I'm looking at the first derivative. And I'm going to put it here because I have room. So the first derivative was 3x squared minus 27. And the second derivative was 6x. Again, I need to discover the sign here, the sign here, and the sign here in order to identify what point is this, what point is this. So in this function, I want to plug in -10, I want to plug in 0, and I want to plug in 10. To the left-hand side of -3, I'm going to plug in -10. To the right-hand side of 3, choose any number. I chose 10. It doesn't matter. So, with -10, this will be 100 minus 27. What is the sign here? You can put in the function in the graphing calculator and plug it in. But this is too easy. With -10, -10 squared is 100, not -100. -10 squared is 100 times 3 is 300 minus 27. What is the sign here?
Positive.
Very good. Now with 0. What is the sign of the first derivative with 0 plugged in?
Being negative.
Excellent. Finally, with 10 plugged in. Three times 100 minus 27.
Positive.
Excellent. Now we draw our conclusion. Can anyone tell us what type of point is negative 354? And before you say anything, don't say anything just yet. Let's take a look. From negative infinity to 0, what does the function do? From negative infinity to 0. Does it increase or decrease? From negative infinity to 0.
Increase.
Is this supported by the sign of the first derivative? Is it supported by the sign of the first derivative? So from negative infinity to 0, the function is increasing. Is that supported? Does the derivative say the same thing or not?
No.
The derivative is positive. If the derivative is positive, the slope is positive. If the slope is positive, the function goes up. Right? It's positive. So it's perfect. The two rows work well together. What about from 0 to 54? Is the function increasing or decreasing? From 0 value to 54 value, increasing or decreasing?
Increasing.
Perfect. Is it supported by the sign of the first derivative? Excellent. From 54 to 0, what does the function do? Good. Is it supported by the sign of the first derivative? Correct. From 0 to negative 54, it's decreasing, and it's supported by the sign of the first derivative. From negative 54 to 0, it's increasing, yes. The derivative says the same thing. From 0 to infinity, yes, the derivative says the same thing. So the two rows work perfectly together. But now I need to make a decision. What type of point is negative 3, 54? The arrows tell us the story. The sign of the first derivative tell us the same thing. So negative 3, 54. What type of point is it?
Max.
Indeed, it's a local max. Perfect. What type of point is 3, negative 54? The arrows tell us, and the sign of the derivative. What type of point will 3, negative 54 be?
Local minimum.
Very good. Final step. I found a point where the second derivative is 0. Now, this is the second derivative. 6x. Plug in a number to the left of 0, like negative 10, and tell me the sign. Plug in a number to the right of 0, like positive 10, and tell me the sign. That's all I need. I need the sign to the left of this point and the sign to the right of this point for the second derivative now.
To the left it's negative, to the right it's positive.
Very good. Now please understand and remember, if the second derivative is negative, the function does not hold water. If the second derivative is positive, the function holds water. Concave downward, concave upward. Let's see if it makes sense. The function looks like this. From negative infinity to 0. Is it okay for it to have a maximum? Should it have a minimum?
You should have a max.
Of course. Absolutely. And these two work well together. It's a local maximum, so obviously the function has to open downward. On this side, this is our check. We're checking our work. On this side, Is it okay at the critical number with x equals 3 for this to have a local minimum? Are these two working in sync or not? The opening upward with the local minimum, do they work well together?
Yes.
Of course they do, otherwise it will make no sense. If here I get a local maximum and the function actually opens upward, I'll say, oops, I messed up. Now we're ready to graph. We have everything we can think of. Nothing matters but the table. Everything else is redundant. The table, and here's how we read the table. The table tells it all. I have to plot negative 5.20. 1, 2, 3, 4, 5. On the other side, 1, 2, 3, 4, 5. So I plotted negative 5.20 and 5.20. Now I plot 0, 0. Now I plot negative 354. Negative 354, I'm going to say 10, 20, 30, 40, 54. And on the other side, 10, 20, 30, 40, 50, 54. I have all the points. Here's how I read the graph. Please pay attention. It's very simple, but you have to understand this. From negative infinity increasing to the point of intersection. Fine. Further increasing to the local maximum. Fine. Now it's decreasing, still opening downward to the inflection point. Oh, I forgot to mention this. Inflection point, the second derivative changes sign, therefore 0, 0 is an inflection point. So it's opening downward, decreasing to the point of inflection. At this point, it changes concavity because it starts opening upward. It's decreasing to the local minimum. Opening upward, reached the local minimum, crossing the x-axis, 5.2, 0, and going to infinity. This is the graph of x cubed minus 27x. And we have to write that. How was I able to put this all together? From here. I found x and y intercepts. I found the limits at infinities. I found the critical numbers. I studied the sign of the first derivative. I made sure that the two rows go well together. When the function is increasing, the derivative has to be positive. When the function is decreasing, the derivative has to be negative, or vice versa. The derivative is negative, then the function has to be decreasing. They go back and forth. Then I found the second derivative. I found where the second derivative is 0 or undefined. I studied the sign of the second derivative, meaning when the second derivative is negative, the function does not hold water, and this matched with the local maximum. When it's positive, it holds water, and that matched with the local minimum. Once I put all this together, I get this graph. Any questions? Any questions? I want to practice this table with one of, and you can choose any problem you want. I want to practice the table with this. This looks like gibberish. What is all this? I don't understand any of it. Once we summarize it correctly in the table, it will be very clear. So let's choose a problem from here, please.
Lesson 37.
let's look at 37. Perfect. And I am on page 7.